Okay, many thanks to the organizers for this wonderful conference. It's a pleasure to be here. And indeed, the next 15 minutes we'll be spending our time discussing a particular competition between a number of condensates on the Conifold. And all of these different condensates will be contributing to the phenomenon of superconductivity, as is evidenced here in the background. And I should mention that this is based on work in collaboration with my student, Andrea Borghese, sitting over there, and also with Jorge Russo from Barcelona and two of his students, Francisco Aprile and Aldo Dector. Okay, so of course the way we're going to approach this phenomenon of superconductivity is via the holographic duality. So we have just inserted one slide, but I'm sure you've all seen this picture before, so I think it can be very brief. The idea, of course, is that there's different descriptions of D3 branes in some particular background which actually turn out to be equivalent. For instance, on the world theory, the world volume theory of the D3 brane will correspond to some four-dimensional theory, which in the case if the D3 brane is living on some Calabi-Yau manifold, which is the cone over a five-dimensional Sasaki-Einstein base, the four-dimensional theory would be some n equals to 1 super Yang-Mills theory, whereas on the gravity side, of course, the theory would be described by type 2b in the back-reacted geometry, which in this case would be ADS5 cross exactly the Sasaki-Einstein base manifold. So this is all completely general, holds true for arbitrary Sasaki-Einstein manifolds, but there's two cases which are of particular interest for two reasons. The first one is that there are completely homogeneous examples of Sasaki-Einstein manifolds. So these are the S5, which of course was the original example due to Maldacena, SO6 divided by SO5, and the other homogeneous example of a five-dimensional Sasaki-Einstein manifold is T11, which is this particular cosine manifold, which already made its appearance also this morning in Mariana Gragna's talk. The reason that both of these are very interesting is that we know the full spectrum on these spaces. So type 2b on either of these manifolds, we know all the masses and charges of the different modes. So what we're going to do in what follows is we're going to check all the sort of general statements that you can make about this setup for generic Sasaki-Einstein manifolds. We're going to see whether that actually holds true for the two explicit cases of either the S5 or the T11. And in particular, the thing that we're going to look at is superconductivity. So how do we describe superconductivity on the gravity side? Of course, it's a field theory phenomenon. On the gravity side, this corresponds to a particular phase transition between two different phases. So for high enough temperature, the theory is described by some black hole, a particular Reisner-Nordström black hole for high enough temperature. But then it turns out if you lower the temperature, at some point a certain instability arises. And in particular, if you go below this particular critical temperature, then a condensate appears. So the black hole actually grows some hair. Now, what this hair does is that it breaks the U1 symmetry, because this is an instability of some charged scalar field in our case. And because it breaks this particular symmetry on the field theory, or both on the gravity side and on the field theory side, and this will be our working definition of superconductivity. So below this critical temperature, instead of the normal Reisner-Nordström ADS black hole, there's actually a black hole that dominates the thermodynamics with particular hair, and that's the superconducting phase. Now, what's been shown by Gubser and collaborators is that for all Sasaki-Einstein manifolds, that there is such a mode, which is exactly this phenomenon. And it corresponds on the field theory side with an operator which has conformal dimension equals to 3, and its masses and charges are given over here. But one very important point is that there's, of course, many other modes, and all of them could, in principle, have an instability. So to determine which one is going to dominate the thermodynamics, and for that reason are going to determine the properties of superconductivity, in principle, you'd need to look at all of these modes. Now, we've only got 15 minutes, so clearly that's not going to work out. Fortunately, we don't have to look at all of the modes. The only modes that we have to look at are the ones with low conformal dimension. You can check that. Indeed, low conformal dimension gives rise to very low masses, even negative masses, right? So that sort of smells very unstable already. So the ones with low conformal dimension are the ones that are very prone to instabilities. And in fact, you can check that the lower the conformal dimension delta, the higher the critical temperature of that particular instability. So effectively, what it boils down to, what we're going to do in the rest of this talk, is we're going to see whether for the particular cases of the S5 and the T11, whether there are any operators with lower dimension than delta equals to 3, which is sort of the universal mode for all Sasaki-Einstein manifolds. Okay, so let's go to the first concrete example, which is the 5-sphere. So for the case of the 5-sphere, of course, the corresponding Calabi-Yau manifold, the cone over the 5-sphere, is flat space-time. So in this case, we're looking at competing condensates in flat space-time. Now the good news is that the full spectrum of type 2b on the 5-sphere has been calculated already 20 years ago or so, and it's given here in this little plot where I'm telling you as a function of the masses and the charges of these scalar fields. The spectrum splits up into 3 Kaluza-Klein towers, and of course the ones at the bottom of these Kaluza-Klein towers have the lowest conformal dimension. Now it turns out that the 3 Kaluza-Klein towers have one mode at the bottom with conformal dimensions delta equals to 3, delta equals to 4, delta equals to 3, and delta equals to 2, respectively. So of course the last one should pique your interest, right? That one actually has a lower conformal dimension than the universal one with delta equals to 3. So for the S5, indeed, there is a mode which in principle has a higher critical temperature and hence could potentially be more unstable than the universal Gapser mode, and hence it could dominate the thermodynamics at a particular temperature. In order to check whether this is true, we need a bit more than what's on this plot, because the critical temperature follows just from the mass and from the charge, which are like the lowest order coefficients in the expansion of the full gravity theory. But whether it actually condenses is a question that's only settled by all the higher order modes as well. So we need more than this information. Fortunately, all of that information is actually captured by a particular gravity theory, because we know that we can truncate type TB on the S5 to maximal supergravity in 5 dimensions. And that includes the bottom of all of these 3 KK towers. So we know the full expansion for this particular mode. Now, given this full expansion, you know more than just the mass and the charges. You know all the higher order coefficients as well. And using these, you can just do the full calculation and see whether this mode actually condenses. So that's what we're going to do in the next plot. We're going to plot we're going to compare the condensation of the red delta equals to 3 to the orange delta equals to 2. It turns out that there's 2 surprises and they sort of cancel against each other. What happens for the delta equals to 2 mode, if you do the calculation of the condensation, that there's only condensation above the critical temperature rather than below the critical temperature. And of course, this is not the way that we normally think about superconductivity, right? Which should be a low temperature phenomenon. So what's going on? Right, so there's only this mode for the hair of the black hole above a particular temperature. If you subsequently also calculate the free energy, you find that it's actually always higher than the normal black hole, the Reisner-Nordström black hole. Right? So it's never going to dominate the thermodynamics. It always has subdominant free energy. So this mode basically is completely irrelevant for the phenomenon of superconductivity, and indeed the delta equals to 3 mode is the first instability that actually kicks in. Right? So the orange mode basically never shows up. 0 points for the orange team. It's just like the Euro Cup. So that's the S5. That was the first concrete example that we were going to do. The second concrete example that we're going to do is the other homogeneous Sasaki-Einstein space, which is T11. Now, also in this case, we have the full spectrum of type 2b on this particular space. It's also been calculated, and again, it organizes itself into a number of Kaluza-Klein modes. So in this case, there's 2 which are in red, with whose lowest, the bottom here, are described by delta equals to 3 and delta equals to 4 operators. And there's 2 orange ones, 2 orange ones which have delta equals to 3½ and delta equals to 5½ Again, beautiful, right? We know that, of course, delta equals to 3½ is lower than 3, right? So this orange mode has a very good chance of condensing before the delta equals to 3 operator. Beautiful. So we'd like to do the same calculation as we did in the previous case. But as I stressed then, in order to be able to do that, we need more than just the masses and the charges. We need all the higher order operators, right? So we need some full gravity theory incorporating all the higher order terms for these particular modes in order to calculate whether it actually condenses or not. Now, this is the bad news. We don't have such a truncation. We don't know which theory exactly describes all the higher order corrections or higher order coefficients for these modes. So what we've done in this particular paper is that we've said assume that this truncation is consistent. And I must say this is a far leap, and it's by no means obvious that such a truncation is consistent. But what we've argued on a number of symmetry principles is that if this truncation is consistent, then we have the unique gravity model describing it. Once you have the gravity model describing it, of course you can do exactly the same calculation as we showed for the 5-sphere before. Right, so that's the big assumption. The big assumption is that it should be possible to truncate consistently only to these modes, and we don't know that that's true. We do know that it's true for this mode. You can truncate just to the bottom of this Kaluza-Klein tower. For this tower, it's an open question, and we have a number of reasons to believe or to argue why this is true, but it's certainly by no means settled. If you buy this assumption, we think we have the unique model, and hence you can check whether it actually condenses. Lo and behold, indeed, it does condense in this case. So the delta equals to 3 mode is here. The delta equals to 3½ mode, of course, is up here because we know that it has a much higher critical temperature based on the masses and the charges. And given the explicit gravity model that we propose, you can check that indeed there is a corresponding solution where this mode has a particular condensate below this critical temperature. And checking the free energy, you see indeed that this always is going to dominate the free energy for all temperatures below this particular temperature. So if the truncation to this delta equals to 3½ mode is consistent, then it will always dominate over the universal delta equals to 3 mode of Gapser. Okay, so that's the conclusions. The fate of holographic superconductivity is, I think, determined by a competition between a number of condensates. Gapser showed that there's always a universal delta equals to 3 mode for all Sasaki-Einstein manifolds. But we've checked in 2 specific cases, the S5 and the T11, that there's always modes which in principle have a higher critical temperature. And this is associated to them having a lower conformal dimension. So in the case of the S5, there's a mode which has delta equals to 2. So in principle, it has a higher critical temperature, but it turns out that it never condenses. It's always subdominant in terms of thermodynamics. In the case of T11, there's also a mode with a higher critical temperature. That's the delta equals to 3½ mode that I showed you. In this case, in order to check condensation, you'd have to know the full model. We've made a proposal for this full model, and it's based on the assumption that you can actually truncate to this bottom of the KK tower. If you buy that assumption, then indeed it does condenses first. So indeed, this mode will always dominate the thermodynamics. So the open questions, I think, are very, very obvious. The first one, of course, how robust is this assumption? So we have a number of arguments, and in particular, there was thought to be a no-go theorem to truncate just to this particular mode, but we think we can rule out that no-go theorem. We can just circumvent it. So then we use the mathematical inequality that minus minus is plus, so no-go must be the same as go. So because of that, we just boldly wrote down the model and we did the calculation. If it's true, that'd be very interesting because that would mean that there must be a new mechanism to do consistent truncations, and this would be a new mechanism similar to the ones for the 5-sphere truncation. If it turned out to be inconsistent, then clearly the calculation that we did is not necessarily correct anymore. But I think the instability still is there, right? So in that case, it would just be described by different dynamics, and you'd have to check that according to that whether according to that dynamics it condenses or not. Okay, that's it. Thanks.
Thank you. Questions? Yes.
You had on the picture you had delta equals 3½ and delta equals 5½. So
Yes.
Is this lowest point, is it just one object?
No, it's two. It's two, in fact.
And
Yeah.
why don't you have to consider that at the same time?
We did, but it turns out that in that case, in fact, it's very interesting because this one turns out to lead to a second-order phase transition. This one turns out to lead to a first-order phase transition, but at a much lower critical temperature. So this one, the delta equals to 5½ always loses out to the delta equals to 3½ in a very interesting way, which unfortunately I didn't have time to introduce, but we did include it, and it never wins.
More questions? Yes.
Have you any clue about which truncation could be, or you have really no idea, or you are investigating something?
No. There's a number of ideas. So the thing is that for the type 2b on the 5-sphere, of course, in the end you're led to maximal supergravity, right? But there's a sort of consistent truncation of that theory where you just reduce the metric and the 5-sphere on a particular manifold, which is SL, so well, it's the on the 5 sphere, right? That already gives you a clue of what the field content in 5 dimension is going to be. Doing exactly the same thing for the T11. T11 is also a coset manifold, and just based on that structure, you can already argue that the field content in 5 dimensions should at least include some SU2,2 structure. So the modes that are given here should be included. Some of these modes, the ones that you're going to retain, should be included in that SU2,2 scalar manifold. So we're trying to, but of course, to prove the full consistency is highly non-trivial, right? And even for the 5 sphere, I'm presenting it as if it's been proven, but it's not really been proven in full generality. In fact, everybody believes it must be true, but to actually prove it is highly non-trivial, and it hasn't even worked out for the 5 sphere.
Okay, I think we should move on, so let's take it.